It's often the case in mathematics that two varying quantities will change with one another. If we're talking about a constant rate of speed for an automobile, then time is related to distance. That is, as time changes, so does distance. If a person is working for an hourly wage, then the number of hours worked corresponds to the amount of a paycheck at the end of a week. Well, this creates an idea for a relationship between variables. And the notion of relationship leads to a very special kind of relationship mathematically called a function. We're going to define function here, and there are a lot of different ways to define function. This is the easiest one that I've ever seen. All the definitions, though, are consistent with one another. All right, first of all, let's define the notion of relation, and we can think of it as relationship. A relation is just a set of ordered pairs, and there may be a relationship between those ordered pairs, you see, between the items in the ordered pairs. All right, so if a relation is a set of ordered pairs, then a very simple relation would be the set consisting of these three ordered pairs. There's a relation. All right, back over here. Let's define domain of the relation, of our relation here, as the set of first elements, and range as the set of second elements. So the domain would be the set of first elements. Well, that's just 1, 2, and 3. The set consisting of 1, 2, and 3. The range is the set of second elements. Well, that would be the 2, 4, 6. You see, domain and range. Now, you may be asking, well, gee, why did I use the words first element and second element? Why didn't I just say the domain is the set of x values and the range is the set of y values? That's all there is to it. If we're talking about x-y pairs here, well, yes, that's true in this particular situation. But we don't want to confine ourselves to an x-y kind of relationship. There may be a distance-time relationship, you see, a d and a t relationship, and other letters may be involved in the idea of relation. So we don't want to limit ourselves in that way, and that's why I use first element, second element. But for conversation purposes, it's okay for understanding to think about x and y in terms of domain and range. Okay. Now, a function is just a special kind of relation, and here is a definition. A function is a relation in which every element in the domain, every value of x, if we're thinking of x's and y's, corresponds with exactly one element in the range. So a function is just a set of ordered pairs in which for every value that x takes on, there is exactly one value that y takes on. All right, sort of using primitive graphs, the situation looks like this. Now, in our domain and range values here in the previous example, we had 1 associated with 2, 2 associated with 4, 3 associated with 6. Now, do we meet the definition of function for this particular relation? Well, let's see. Is it true that for every element in the domain, there is exactly one element in the range? Well, does this guy have one partner over here? Yep. Does this guy have one partner over here? Yep. Does this have one partner over here? Yes. So this is a function type of relationship. How about this one? Now, notice the correspondence here. We have 7 corresponding with 4, 8 corresponding with 5, 9 corresponding with 5. Do we meet the requirements of function? It turns out that we do here, because every element in the domain corresponds with only one element in the range. Now, these two guys happen to be corresponding with the same element in the range, but that's okay. You see, we have only one value in the range associated with 8, only one value in the range associated with 9. And by the way, there could be other items in the range. The range could include 1 and 10 that have no correspondence with items in the domain. It's okay. If we had other items in the domain, though, we would need to have partners in the range corresponding with them. That's this idea of exactly one. That means one and only one. So we have to have a partner and only one partner, you see, in the range for us to have a function relationship. All right, here's an example of a non-function relationship. We have 7 and 8 in our domain, and the range consists of these elements. And the correspondences are 8 corresponds with 6, 7 corresponds with 4, 7 also corresponds with 5. And this situation is what causes this to be not a function relationship, because 7 corresponds with 2 items in the range. Now, we're going to look at a lot of different ways to describe relationships. You know, we can describe relationships in mathematics between variables with ordered pairs. We can describe relationships sort of verbally. We can describe relationships graphically. We can describe relationships with an equation. And we're going to take some time here and talk about function versus non-function in all of those various situations. Here we're looking at ordered pairs. Now another way to kind of look at the situation, it's kind of paraphrasing what we have here, is this, that every value that x can assume is associated with only one y value. You see, it's the same exact idea. We just don't like to confine ourselves to x's and y's. And by the way, I'll tell you also that this definition in some textbooks for domain and range describes them as independent and dependent variables. And that's not too foreign to us either. If we're talking about building a table of values, and you know, we build our table of values, we put an x and a y, and we have columns, and then we choose at random values of x, a lot of times, and then we generate values of y according to the values of x that have been chosen. So we can think of x as, those x's that we've chosen, as being independent. They're just chosen out of the sky. And then the values of y that come out of that turn out to depend on the values of x that we've chosen. So we can say that the values of x are independent variables or independent values, and then the values of y are dependent. So that there's a nice correspondence with our experience there. All right, let's look at a few situations. Here's an equation, and we're going to go through the process of identifying domain and range here and deciding whether or not we have a function kind of relationship in our equation. Now, in our past experience, domain was kind of loosely described as acceptable replacements for x. And that's very consistent with our idea of domain here. Domain is all of the set of first elements, you see, if we're talking about ordered pairs. And for equations, it's for what values of x is this relationship or this expression defined? Well, gee, this makes sense for all values of x. For all real numbered replacements for x, 2x minus 3 makes sense. So the domain is all real numbers. And it turns out that the range is all real numbers as well. That is, y can take on values for all real numbers as x changes value in this process. All right, let's get to something a little more interesting. How about y equals the square root of x minus 3? Aha, now we have a domain that's not all real numbers, because the acceptable replacements for x are those values of x for which the radicand is positive or 0. So that means that x can only take on values greater than or equal to 3. So the domain would be x is greater than or equal to 3. Now the range is pretty easy to identify as well. When x takes on those values 0 and greater than, x takes on values 3 and greater than 3, the radicand is 0 and all positive numbers. All right, now what do we get when we take the square root of 0 and all positive numbers? Well, y would be positive, that's all, or 0. So the range is y values greater than or equal to 0. Now, we're not here, though, to talk about domain and range. We're here to talk about whether or not we have situations involving a function. So let's make that decision. And we make the decision according to the definition. Does it meet the definition of function? Well, let's see. Is it the case that for every single x that we choose in this group of numbers for the domain, for every x that we choose, we get exactly one value of y? That is, if x is replaced with 10, we would have 2 times 10, 20. 20 minus 3, 17. So y is 17 when x is 10. Is there any circumstance where we would have an x replacement here and 2 values of y? No! And therefore, this does represent the function idea. That is, y is a function of x. What about here? Is it the case that every time we choose a different x, we get only one value of y? Well, yes, that's certainly true here. If x is 4, 4 minus 3 is 1. Square root of 1, the principal square root of 1 is 1. So that ordered pair is in our solution region here. It's part of the graph here. And it illustrates the idea that one value of x give rise to or causes only one value for y. Now consider this equation. Now this equation does not represent a situation where y is a function of x. And it doesn't, because of this, it doesn't meet the definition. And here's why. All right, if we take this and solve it for y, then using the square root property, we find that y is plus or minus the square root of x minus 3. Now let's let x take on a value like, oh, let's say 4. So we would have, let's see, 4 minus 3 is 1, square root of 1, plus or minus the square root of 1 is plus or minus 1. So when x is 4, y is plus or minus 1. So it means then that two solution points associated with this equation, two coordinates that cause this to be true are 4, 1 and 4, negative 1. It means for a single value in the domain, there is more than one value in the range associated with it. So here, y is not a function of x. There is a rather special notation associated with functions. Consider this equation, y is 2x minus 3. It does turn out that y is a function of x here. And function notation associated with this could be f of x is 2x minus 3. Now I read this f of x, but it doesn't mean f times x. F is just the name of the function. Now that name could be George or any other kind of name, but George has too many letters, so we just use a single letter for the name of the function. And x is the variable that we see here. So f is the name, x is the variable. Now the name could be f, g, h. Those are kind of traditional letters used to name functions. Now if we interpret this f of x in a particular way, then this notation leads us to a technique for evaluating functions for a particular value of the variable. Now we can interpret this as the value of f at x, you see, and if we pop in a value, a particular value like 4, then this means in the f function replace x with 4 and evaluate. We're finding the value of f at 4, you see, and we would then make the substitution, replace x with 4 and evaluate. And let's see, that's 8 minus 3 or 5. Suppose we make the request of f of x minus 3. Then this means in the f function, replace x with x minus 3 and evaluate. So let's replace x with x minus 3. Now we're replacing this x with x minus 3. So instead of 2 times x, it's 2 times x minus 3, and then minus 3, you see. So we have 2x minus 6 minus 3, or 2x minus 9. Here's another one. This function's name is h, and the variable is t. So h of t is equal to this expression. H of 3 means in the h function, replace t with 3 and evaluate. So let's see, this t is replaced with 3, and this other t is also replaced with 3. So we have 9 minus 6, or 3, as h of 3. Here we have h of t plus 2. It means in the h function replace t with t plus 2. So we have, let's see, t plus 2 squared minus 2 times t plus 2. And away we go with evaluating, just simplifying here. Now, before I go on with that, though, I want you to realize that this letter could be r. If this were r plus 2, we would put r plus 2 here and r plus 2 here. Doesn't have to have the same letter correspondence as we had up here. It could be a different letter. It could be any number of things. And it's important to think of this replacement here as kind of a blind replacement. All you want to do in the first step is blindly replace the letter you have up here with whatever is in this parenthesis. That's kind of the way you want to think about it. All right, let's see. Squaring here, we get t squared plus 4t plus 4 minus 2t minus 4. And collecting here, t squared, 4t minus 2t, 2t, 4 minus 4, oh happy day, they go out. So this is h of t plus 2. Here's another one. What if I requested h of oh, let's say, happy face. Now here we have to think of this as a blind replacement. We're blindly replacing t with the happy face. So it would end up being, well, let's see, we have t squared minus 2t, so it's happy face squared minus 2 times happy face. There we go. Here's a function that is defined differently over two different intervals of its domain. It's called a piecewise function. It's defined in pieces, if you will. F of x is this expression when x is less than or equal to negative 1. But f of x is minus x plus 4 when x is greater than negative 1. So these are the definitions for domain, and the function is defined this way in that domain, that part of its domain, and this way in this other part of its domain. All right, what if we want to evaluate f of negative 2? Well, we have to figure out where negative 2 falls in terms of domain. Well, let's see. For x values less than or equal to negative 1, negative 2 would be in this region, and so we'll use this expression for evaluation purposes. So f of negative 2 means in the f function replace x with negative 2. So here we have, let's see, negative 2 squared plus 2. So this will be 4 plus 2, or 6. F of 0, well, where does 0 fall? Well, let's see, would it fall into this region of x is less than or equal to negative 1? No. Would it be in this region where x is greater than negative 1? Yes, it's in this region, and therefore we use this expression for evaluation purposes. So f of 0 would be minus 0 plus 4, or simply 4. F of negative 1 itself. Now notice that negative 1 is that very special point where we change the definition for the function. So it's important that we pay some attention to where we are in terms of a strict or non-strict inequality here. F of negative 1, let's see, this is for x values less than or equal to negative 1, and that's where we are here, so we're going to use this expression. So we would pop in negative 1 squared plus 2. Negative 1 squared would be 1, 1 plus 2, 3. And then f of 3, 3 is in, let's see, it would be in this region of x is greater than negative 1. We'll use this expression. So we have negative 3 plus 4, or 1. A piecewise function. Let's get back to the notion of identifying domain involved with some functions. Now, we looked at a situation earlier where we had a radical involved for the expression associated with the function. We didn't call it I don't know if we call it, yeah, we were calling it a function at that time. And we identified the domain as acceptable replacements for x. And we went about identifying that domain by simply saying, for what values would that radicand be positive or 0? And that's how we made the identification. Now here we're going to do a very similar kind of thing. When fractions are involved and variables appear in fractions, we have limitations on the domain. Generally we say that the domain, or the acceptable replacements for x, would be all real numbers with some possible exceptions. And we're really identifying the exceptions here. Here the exceptions would be those values of the variable y that would cause this denominator to become 0. And this denominator is 0 when y is negative 5. So the limitation is that y can't take on the value of negative 5, so we say y is not equal to negative 5. Now, a more formal way to write this domain, this is a rather informal way. We're kind of assuming that it's all real numbers except this particular one, you see, and we know that by just the nature of this notation. But another way to do it would be, and this is a little more formal, it would be the set of, see, the domain is a set of numbers, so we can say the set of y values such that, now y, I'm using y because that's the variable used in our particular function. So the set of y's such that y is an element of the real numbers and y is not equal to negative 5. You see, that's a much more formal way to do it. Here's another one, h of x is 10 over this expression. We want the domain. But to identify domain, we really just need to identify the limitations on the domain is what we're really after. And those limitations are values of x that will cause the denominator to become 0. Well, we can see those values much more clearly if we see a factored form here. So we would probably go through a step to factor, and we take out a common factor x, and we have x squared minus 2. Wow. All right, we have the values of x that will cause each factor to become 0. Well, it's pretty easy to see that when x is 0, that factor becomes 0. So we know that our limitation on the domain is that x cannot be equal to 0. Well, what about this other one? Well, that's not easy to see. We don't have the difference of squares here, so we can't really factor further. But we can do this. We can think, well, I'd like to know the values of x that will cause x squared minus 2 to be equal to 0. And now I can solve this by doing this, add 2 on both sides, and now by the square root property, x is plus or minus the square root of 2. So our other limitations are x cannot be equal to the square root of 2, x cannot be equal to the negative of the square root of 2. Here's an interesting problem, and it is along the same theme that we were talking about before. That is, we're talking about functions here. But a lot of mistakes are made in this kind of, in the wording of this kind of problem. It says, f of x is this. For what values of x will f of x be equal to 0? Now, we're not talking about the domain here. It just says, for what values of x will f of x be equal to 0? Now, the way to deal with it is that, gee, we want the values that will cause f of x to be equal to 0. So all we do is take this expression, or this equation, and replace f of x with 0. You see, take this f of x and replace with 0. They're equal to one another, so they are replaceable with one another. So we would have 0 equals x cubed minus x. And now here's our request. For what values of x will f of x be equal to 0? You see, and now we're just factoring here. And we get this, and factoring further, we find that for these values of x, f of x is 0. I want the value of x that will cause each factor to be 0, and that would be 0 plus and minus 1. Here's a rather special calculation dealing with the function notation. It says for f of x equals this expression, find f of x plus h minus f of x all over h. Now, this rather special form is called a difference quotient, and it's used often in calculus. Now, the evaluation goes like this. This says, in the f function, replace x with x plus h. So here we go. Just with this part now, replace x with x plus h. So we would have this x and this x are replaced with x plus h. You see, we're going to write this whole expression and replace x with x plus h. So we'll have x plus h squared minus 4 times x plus h plus 7. All right, this then is f of x plus h, because we've taken this expression, and for these two positions of x, we have replaced with this binomial. So binomial squared minus 4 times binomial plus 7. Binomial squared minus 4 times binomial plus 7. And it's really important, if you're evaluating these rascals, these difference quotients, to really take that much care in the substitution idea. That's where all the mistakes are made. Once the overall substitutions are made, then very few mistakes are made. All right, minus f of x. Well, f of x is this expression. So it's minus the f of x expression. Now, notice I've introduced a parenthesis here because I'm writing a trinomial. And I want to make sure we're talking about subtracting the entire trinomial and not just the first term of it. All right, and then all of this is over h. Now notice, no function notation in this denominator. All we're doing is writing h. All right, all the action is in the numerator here. Let's see, x plus h squared, that's x squared plus 2xh plus h squared. Then minus 4 times x plus h is minus 4x minus 4h plus 7. And then minus all of this means change all those signs. We have minus x squared plus 4x minus 7. All of this is over h. Now, typically, some very nice things happen algebraically here in evaluating difference quotients. For example, I have an x squared here, and I have an x squared here. So I have x squared minus x squared. Those go out. And then I have, let's see, 2xh and no other xh's. So I have 2xh left in the numerator. I have h squared here and no other h's. So I have plus h squared. I have minus 4x plus 4x. Those go out. I have minus 4h and no other h's. And I have 7 and minus 7, those go out. So a lot of things kind of drop out by themselves, and then all of this is over h. Now h divides every one of these terms in the numerator. That's one way to look at it from here, or I can just factor in the numerator, pulling out an h, a common factor of h. Now if I pull out the common factor of h, let's go out to the side. H is here, here, and here. So I have h times 2x, h times 2x plus h minus 4 all over h. These go out, and I have this numerator as the result of all of this. So it's kind of algebra intensive a little bit, but the key is the replacement here in the very first step, this f of x plus h. In the f function, replace x with x plus h. So just imagine this binomial going into both of these slots and writing down the whole expression like that. That's the key. Here's a problem involving the writing of a function. It says a rectangle is bounded by the x-axis and the semicircle y equals the square root of 25 minus x squared. Express the area of the rectangle as a function of x and determine the domain of the function. Well, let's first talk about what it means for a rectangle to be bounded by the x-axis and a semicircle. Now here's the semicircle, and of course the x-axis is along the bottom. The rectangle could be configured in a number of ways. Just notice that the top of the rectangle is bounded by, or the corners touch, that semicircle to cause the particular configuration that we have for the rectangle. And since we have a changing configuration of rectangles, we certainly have a changing idea for area as well. Now the area depends upon the value of x. That is, as x changes value, as x changes along the x-axis, the size of the rectangle changes. For example, for this x, here's the rectangle that corresponds to that particular x value. And this kind of problem, by the way, represents the essence of the notion of function. We have a variable quantity x, and that quantity is determining a different value of the area. Every time x changes, the area changes. All right, for us to write the area in terms of that x value, we begin with the area formula. A is LW. Now understand that the length of our rectangle is really two values of x. Here's the value of x, and here's another value of x, or distance of x, on the other side of the y-axis. So those two distances together really give us the length of the rectangle. The length then can be expressed as 2x. The width of the rectangle is the distance from the x-axis to the semicircle. Well, that's simply the y, the vertical distance here, but we know y is the square root of 25 minus x squared. So here's our area in terms of x. And if we want to write this in function notation, we could write it as a of x like this. Now we're ready to determine the domain.
The domain is determined according to the nature of the function at hand. This function only makes sense when the x values are positive, because only positive x values will give us an area that is positive or 0. At the same time, we want to make sure that our radicand is positive or 0, because that's the only time when the radical makes any sense. And the radicand is positive when x is less than or equal to 5. So our domain would be x's between 0 and 5. Well, let's take this problem a little bit further. I'm a little curious about the largest rectangle possible. That is, I'm curious about the largest area that we can possibly make here for one of these rectangles, and the x that would cause that kind of situation to occur. Now, in order for us to investigate this, we can use a graphing calculator, and to put this onto the graphing calculator, we'll think of a of x as y, and we'll enter this equation onto the graphing calculator. I've already entered the equation here.
Let's look at window settings.
Now, I've set the x minimum at 0, x maximum at 5, and notice the y minimum at 0 and the y max of 27. And the graph looks like this. Now, understand that this is a graph of actually the area, because we are relating an x value to a y value, which is the area of the rectangle, and we want to maximize our area. So let's go to the top of our graph using the trace button. I'm cursoring to the right now to get to the top of our graph, and I'm looking for the largest y value that comes up on display as I continue to cursor to the right. And I believe that largest value, I'm going to go back just one here.
Here it is, 24.997.
About 25 for the largest possible area, and that occurs at, rounding to the nearest tenth, at an x of 3.5.